Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology. Hope that you are all having a wonderful week, and thank you for joining in on today's webinar. This webinar is being recorded, and for those of you who are uh, listening in on the recording, thank you for listening to the recording. Anyway, today I'm going to be talking about the project that um, Saudi Aramco worked on many years ago using AFT Mercury to help automatically size a seawater pipeline in Saudi Arabia for oil injection uh, or oil recovery purposes with water injection. And this webinar is actually based upon a technical paper that we have on our website. And so I want to show you all where you can find this technical paper because it contains a lot more details of the project. So if you go to our website, aft.com, under the Learning Center is where you can find a lot of things, and the technical paper is going to be in Technical Papers. Once you get to that page, the article is currently all the way at the bottom, and it's called Optimization of Seawater Pumping System. And if you click on this link, you'll be able to read some information about the technical paper, and then a PDF of the paper is available right off of our website. And it was presented for the Pump and Turbo Symposium back in 2008. Can't believe that was 11 years ago already. And so I want to go through and summarize this project today and kind of talk about what they did. And this is where you can find the original technical paper right off of our website. Now, before I jump into things, the original intent was to kind of recreate the model that was built in AFT Mercury and bring it into AFT Fathom using the new ANS automated network sizing module, and very quickly realized that this is really outside the scope of a webinar, and so that's where I wanted to focus on, just talking about the project details. This is their what was their AFT Mercury model, which I have brought into AFT Fathom. And as you can see, there's like 35 scenarios here. So the technical paper talks about, things in a very simplistic manner, and there is a lot more that was going on behind the scenes with the actual project analysis, different design cases and different design changes. And so what we'll be talking about later today, you'll see that there are some things that needed to be iterated on even outside the software. And so that's where the focus is going to be on the project today. So with that, I'm going to go ahead and get started here. And let's see if I can switch to one of my different monitors. Let's see here. Okay, perfect. So that is being displayed now. So just a really quick recap for those of you who may be unfamiliar. These are all of our different products that we have available. This is kind of boilerplate information I usually include for every webinar. I'm not going to spend very much time going on that today. You can also find details about all of our software products on our website. So today what I'm going to talk about is the background of what was going on with the project, a overview of the study that Saudi Aramco did with AFT on this project, what the model development looked like, and then we'll go over what the optimized results were and some discussion points, and we'll go over the recommended system that was built. And so let's go ahead and jump into things here. Saudi Aramco was tasked with a project to increase oil production in Saudi Arabia. And they were going to do that through the use of water injection. So they would inject very high pressure water back into the oil reservoirs to help recover more oil out of the wells. And so in order to do that, they were using seawater, and they had to get the seawater to the oil fields because the oil fields are very far away from the coast. So this is where the goal was to determine the optimal pump configuration of their system and to size a new pipeline for transferring the seawater for the oil reinjection. The total pipeline length was about 90.5 miles long, all through Saudi Arabia. The initial flow rate that they were operating at was 2.14 million barrels per day. The goal was to examine what the costs would be based upon either trying to minimize the first cost of the initial design or trying to minimize the life cycle cost over 20 years. So here's where things are geographically. This is Saudi Arabia, and the oil fields are on the eastern side of the country over here. And so this is the Ghawar oil fields, and there's tons and tons of oil reserves. It's the world's largest, producing 4.5 million barrels a day. Well, it was the world's largest back in 2008. I don't know what the largest oil field is now, but in 2008, this was the largest. So the project was to pump seawater from Ain Dar over to Khorais, which I'm certain that I'm not saying the names of those cities properly, but that's essentially where the pipeline is traveling from, is the coast in the Persian Gulf, where tons of seawater is, and they're pumping it 90 miles away to the oil field northeast of Riyadh. So that's where things are geographically for their oil fields. So here's their initial design. Is from the seawater treatment plant, they were going to operate two supply pumps in parallel, both operating at the same time. And then this is the 90-mile pipeline here. And it was a well-engineered initial design where the entire pipeline was going to be 64 inches in diameter. Then they would have 3 booster pumps to boost up the pressure a little bit so that there's enough suction pressure to get it to re-injectable pressures for the wells. So that's what their original design looked like. And it was done really well. They had original supply pumps, three booster pumps. Now, they wouldn't be operating all 3 booster pumps at the same time. They would have 2 booster pumps running, 1 spare. And then they would have 5 injection pumps operating simultaneously. And again, the original pipeline was all going to be 64 inches in diameter, and the entire wall thickness was going to be just over a 1/2 inch thick wall. Here's where AFT came in, is with the ability to help them consider multiple cases of different pipe diameters and different wall thicknesses to be able to figure out if there was a better operation available that could help boost production flow rates and also minimize costs while staying within the requirements. And there's a way that you'd be able to look at a system and determine if there were significant savings opportunities. That's really important to do when you're designing the system and you have the flexibility to be more selective on what pipes are going out there in the field. So that's where AFT Mercury was used, was to do the automated sizing processes of the pipeline in order to minimize either the initial cost or the life cycle cost. Now, that's putting things very, very simply. As you saw very briefly in the model that I showed with AFT Fathom, there's 35 scenarios. And the technical paper really talks about 3 to 5 of the different design cases in a little bit of detail, and there are a lot of other cases that were examined that were not very much documented in detail in that paper. And so this is just putting things very simply. The original design called for using X60 type of steel, which is a pretty strong steel, and that's what they were going to use for the 90-mile long pipeline. In order to figure out the true minimum cost, they had to look at trade-offs between their overall system pressures, how many pumps are operating, what their diameter of the pipeline was, and the overall wall thickness, because they had different design requirements in place that would dictate how much piping they had to buy. And there was a balancing act between the initial cost of the steel versus how much pressure they're able to withstand. And so that's where having a software tool like AFT Mercury and now AFT Fathom with the ANS module makes this much, much easier to accomplish. So in terms of the pumps that they're looking at, when they were sizing the pipeline, they were looking at 3 different types of pumps for the supply, and all of them were going to be gas turbine driven, with 2 of them operating in parallel. And then they were looking at 4 different types of pumps for the booster pumps, and again, that's where 2 of them would operate in parallel, 1 would be spare. And after going through a whole bunch of iterations and automated sizing processes, what AFT Mercury was able to find is that it was able to reduce the piping diameter down to 60 inches in diameter, and it eliminated a whole entire pump station for all those booster pumps. So here's how it did that, is it used a higher strength type of steel. So instead of using X60, which had a yield strength of about 60,000 psi, they considered using X70 steel with a yield stress of 70,000 psi. I think I misspoke. I said yield strength. I meant to say yield stress. So they picked a higher strength of steel. The reason why is because they were trying to balance using a smaller diameter pipeline with maybe a smaller wall thickness, which could withstand higher pressures because it was a stronger grade of steel. And so even though a stronger grade of steel would cost more, less piping material would be needed for a smaller wall thickness, also for a smaller diameter pipe. So the increased cost of the strength was heavily offset by the reduced wall thickness that was needed. In addition to considering the higher strength steel, they also considered different pipeline diameters of either 56 inches in diameter, 60 inches, or 64 inches. Give me just 1 second here. Hold on. Excuse me. Sorry about that. So those are the 3 different diameters that they were looking at. Smaller diameter was less steel, but that would increase the pressure losses throughout the system. And so there were 2 different wall thicknesses that they were going to allow in the pipeline design. The idea was to use a larger wall thickness in the upstream part of the pipeline that would withstand the higher discharge pressures from the pumps. Then later down the pipeline, as the pressure is dropping along the profile, the thought was to use a smaller wall thickness later downstream. That way, a smaller wall thickness would be needed because the pressures wouldn't be as high. So in addition to considering different pipeline diameters, they were also considering using 2 different wall thicknesses to help reduce the costs even further and achieve some significant savings. So that's what the idea was, and it was a bit of iteration that was required to figure out where that transition point was. So how far down the pipeline would a particular wall thickness be used before the transition point to a smaller wall thickness? That was something that had to be examined, and different cases were looked at in those 35 different scenarios to figure out the sweet spot of where that transition point was. So that's also one of the things that they talk about in a little bit more detail in the technical paper. And this eliminated the booster pumps. Now, again, as I mentioned, the original design case was designed for 2.14 million barrels per day of seawater. Now, this was designed for a 20-year pipeline life, and the idea was 10 years down the road, there was thought that they would want to increase production of seawater from 2.14 million barrels a day to 3 million barrels a day. So this is the future operation design case that they were able to look at in good detail from the very beginning. So here was a assumed increase in flow rate to 3 million barrels a day after 10 years. This would require using a parallel loop. Well, I guess maybe not required, but using a parallel flow path was really helpful. The reason why is because it helped reduce the pressure loss in the main pipeline. So there'd be a amount of pipeline where there'd be a parallel flow path that reduces the flow in each leg and overall reduces the pressure loss before the parallel loop would tie back in at the transition point. Now, a key thing I want to point out is for these future operations, this did actually require the use of booster pumps. So for the original design of 2.14 million barrels per day, based upon a 60-inch diameter pipeline, they did not need the booster pumps. But in considering higher flow rates 10 years down the road, that's where booster pumps were required, because with the higher flow, there were still too high of pressure losses in the system, where by the time that the flow gets to the injection pumps, that suction pressure still had to be boosted significantly to injection levels in order to avoid any cavitation problems of the injection pumps. So this system considered using a pipeline with a parallel flow path. Now, one of the ideas in order to help with this was in the original design for 2.14 million barrels a day, rather than just jumping from 2.14 all the way up to 3, they decided to build in some additional flow capacity. So we'll see one of the cases later where they actually looked at a flow rate of 2.5 million barrels per day as well with their original design, and we'll see what that implication had. So here's the system requirements they had. The maximum allowable operating pressure is based upon the yield strength of the pipeline, the pipe diameter, and the wall thickness. So you all are familiar with this equation for the MAOP, and they put a constraint in such that the maximum design pressure would be 95% of the MAOP. So that's one of the design requirements that they threw into AFT Mercury. And then there was also a wall thickness design requirement. In order to make sure that the wall thickness was strong enough, they set a design requirement such that the ratio of the diameter to the wall thickness had to be less than 120. Third, these design requirements needed to also be met under no flow conditions. So essentially, if the pumps were deadheading, the pipeline would need to be able to handle all of that. This is what the elevation profile looks like for the overall, pipeline. And so the pipeline was built with the elevation profile. So it starts off at just a little bit higher than sea level, and then it increases to 900 feet, drops back down, and then goes back up. And so there's a total elevation gain of about 890 feet throughout the 90-mile pipeline. So that's going to also dictate what the pressures in the system are going to look like. Here are the costs that they assumed. They based the pipeline cost on weight. So the entire pipeline cost would be $1.50 per kilogram. This is really, really useful because it makes it a lot easier to account for the pipeline material costs. Let me show you how you would be able to do this in AFT Fathom. So I'll take a quick sidestep here back to the model. So if I was to go into my database here, I would want to create a cost database for my pipe materials. And so let's just use steel piping as a reference. So if I want to tie cost information to steel piping, the reason why I would want to use dollar per kilogram perhaps is because I can click on the material level and go to new cost and change this to mass. And that makes it so much easier because it's just a single cost, and that applies to all sizes and all types within that single material. Otherwise, the way that you would have to create your cost information would be maybe sorting things by type or schedule and then nominal size. So let's say you only want to consider standard schedules, XS schedules, and XXS schedules. Well, here you've got extra strength here, and you would need to click on any of these and do a new cost. And when you're not doing it per mass, there's a lot more information that you would have to plug in here. So doing dollar per kilogram makes things a lot more streamlined and simplified. All right, back to my slide here. Okay, so that's what the material cost was. Now, as far as installation goes, there was cost to install the piping, and there was also cost to coat the piping. So you could either include both of those costs as a type of installation cost, or you could add them together and just lump them in together. As far as energy costs goes, electricity cost was 3 cents per kilowatt hour. Natural gas was 75 cents per 1,000 BTUs, or 0.002 cents per kilowatt hour. So the natural gas was much, much cheaper. That's why they were looking into using natural gas turbine-driven pumps rather than electric-driven pumps. So they also built in an interest rate of 8.5%. Seawater was the fluid being pumped, and this is the list of all the different cases that they examined. So the original case was their original operating flow rate of 2.14 million barrels a day based upon a 64-inch diameter pipeline, and it required the booster pumps. So several other cases were examined. The first 3 cases looked at different diameters with the booster pumps, and then the second 3 cases looked at the same 3 diameters without booster pumps. Now, these 3 cases is kind of a sub case because this is where the goal was to build in some additional capacity for the original design. This is where using the extra strength or the X70 steel was really helpful because at higher flows, they'd be able to withstand higher pressures. But initially, they're going to try and see if they could accommodate this built-in flow capacity without booster pumps. In the end, they actually did need booster pumps for this higher flow rate, as well as the design case for 10 years down the road, where the flow increased to 3 million barrels a day. So those are 12 cases that they looked at. And here are the results for the best 2 cases. The best 2 cases used a 60-inch pipeline diameter, X70 steel, and it eliminated the booster pumps for the initial flow requirement. That's the 2.14 million barrels per day. So case A was optimized for 2.14 million barrels a day. That used a 0.6 inch wall thickness for the first 36 miles of pipeline. After that 36 miles of pipeline, when the pressures had started to decrease, they're able to then transition to a smaller wall thickness down to half an inch. That way, the rest of the pipeline would be a smaller diameter or smaller thickness, and it would minimize the cost of the steel that was required. Case B, this is the one where they were trying to optimize their pipeline with built-in additional flow capacity. So rather than looking at 2.14 million barrels a day, looked at 2.5 million. So this would require a 0.68 inch wall thickness for the first 45 miles. So a little bit longer with a thicker wall thickness. And then they would transition down to 0.55 inches of wall thickness. So those are the two best cases that were optimized. This just goes to document what the comparisons were for the pump values in terms of pump head pressure and the MPSH to MPSH-R comparisons. And so we've got the supply pumps, booster pumps, and injection pumps. For the original case, that's the 64-inch diameter pipeline. Case A is the 60-inch pipeline, and case B is also the 60-inch pipeline, but including the additional built-in capacity of 2.5 million barrels per day. And so if you look in the MPSH columns here, what this is showing you, the first value is the MPSH that's available and the MPSH that's required. And so in order to get proper pumping back into the injection well, that MPSH had to be really high in order to generate the really high pressures needed for reinjection. All right. So here's the overall total cost of the system for the optimized cases. Bottom line is, if you compare the original 64-inch diameter case with case B, that is saving $100 million in cost over the entire lifetime of the system. So obviously things break down a little bit differently by initial cost. So initially, this is what the pipeline costs. So these are all in millions of dollars. So in order to accommodate the 2.5 million barrels per day for case B as additional built-in flow capacity, the pipeline wall thickness needed to be a little bit stronger all throughout. So there's about $8 million of savings here versus case A, which did not have built-in flow capacity of 171 million. And then you can also see what the pumping costs were, the energy cost. So these are pump material costs, and these are the energy cost. And energy cost in the long run is always what dominates the cost of the project. So if you have the ability to start off with a little bit larger of piping, that way you don't need as large of pumps, then you can experience much more cost savings in the long run than simply by trying to make your pipeline or your network as cheap up front as possible. Now, if you take a look at the design for 10 years down the road, this is the parallel flow path, and these are what the costs would be. And as you can see, there's significant amounts of savings by being able to use the automated sizing processes of what was AFT Mercury versus AFT Fathom ANS. And all it did was looked at 3 diameters and a handful of different wall thicknesses. By only considering those things and making some assumptions of lots of commonality, it still saved $100 million on that project. Imagine if you're able to allow a little bit more flexibility where maybe the parallel flow path could have been a different diameter. That could have been used to experience even more significant savings. Yes, it would require maybe a different pipe size in that parallel loop, but you could save more money though. Those are all much easier to look at when you have a automated sizing tool that can look at all the different cases for you automatically. So overall, both first and life cycle costs were reduced. Usually one comes at the expense of the other, but here, because there are several different design cases examined, the design actually was able to reduce both first cost and life cycle cost. And as we talked about before, the higher strength steel allowed higher operating pressures in smaller diameters. And this was the overall savings for case A, which did not built in additional flow capacity early on, 27 million. And then case B, which was initially sized for 2.5 million barrels a day, and then 3 million barrels a day later, saved $8 million from the original design. And then these are the different wall thicknesses allowed better pressure requirements. As mentioned before, the original design, we were able to eliminate the booster pumps with the single pipe diameter, but that's only for the 2.14 million barrel per day case. And that saved significant amounts of energy and maintenance and first cost. But then later they had to be added back in for the higher flow cases. So yes, it eliminated the pump stations, but if you wanted to get higher flow in the system, they were going to need to be put back in. And they do add cost to the system for that at 3 million barrels per day, but it's not significant in comparison to what the original cost was of the overall system. So this is where we looked at the parallel flow path, and it was designed to be the same diameter as the main pipeline and to try and split the flow evenly. Again, if it was allowed to have the outside parallel loop be a different diameter than the main line, that could have saved even more money potentially. And so all those different cases were examined, and they had to figure out where to tie the loop back in. And so the way that they figured out where to tie the parallel flow path back into the main line was essentially by balancing what the pressure loss was in the parallel flow path with the increased amount of pressure loss after the loop was rejoined. So that's how they figured out the sweet spot. And so these are the savings of what that system looked like for the 3 million barrels per day cost. So as you can see, significant amounts of savings there. Now in this 3 million barrels per day case, this is where booster pumps were needed. So it did add $15 million to cases A and B, but overall still there was a significant savings in the long run. So case B was recommended, which was designed for the 2.5 million barrels per day, and later the 3 million barrels with that parallel flow path, and that was built for the system using 60-inch diameter pipeline, X70 steel. The first 45 miles was about 0.7 inches for the wall thickness, and this is what the maximum pressure was at their original flow rate, and then 1/2 inch wall thickness for the remaining pipeline. The parallel flow path used the same diameter of 60 inches and the same initial wall thickness for 37 miles at the higher flow rates before it tied back in. So this is what the pressure profile looks like along the flow path. The red line is the original design case. And as you can see, the original design case, around 75 miles or so, this is where that pressure drops significantly below the reinjection pressure of around 200 psig. And so this is why booster pumps were needed in the original case. When you're looking at just a 2.14 million barrels per day, and you're using the 60-inch diameter pipeline, as well as a stronger steel, you can withstand higher pressures. So that boosted up the pressure profile significantly. And by the time that it gets to the injection wells, those booster pumps were not needed anymore. So that was some really good savings on that original design flow rate. However, when they considered the case for 10 years down the road at higher flow capacities, you can certainly see how both the original case and the new case here certainly does drop below those reinjection pressures. And so this is where booster pumps are needed to help raise those pressures back up for injection purposes at a higher flow. Higher flow means higher pressure loss. So this is steeper than the original pipeline was in terms of the pressure loss. Finally, this is just documenting the pump data that they used for the supply pumps. Again, for the supply end, they were operating 2 pumps in parallel, each one at 31,200 gallons per minute. And then the injection pumps were operating at 12,480. Really high horsepower, really high head generated to really ramp up those pressures to injection levels. And then finally, some conclusions. Where you would apply this with the AFT Fathom or AFT Aero ANS module is if you're trying to work on a design for a brand new system, you want a new project. Well, how are you going to start that new project? A lot of times what you might do is start from your previous project. Use your previous project as a reference point. And essentially what I'm talking about is if I was to switch over to my other monitor here, give me a second. What I'm going to do is I'm going to open up the final case 2B for that system. So this is the final design case for their overall pipeline. I have moved things around a little bit. That's why this looks slightly different than it was before. But as you can see, there's only one scenario because this is the final design case for the 2.5 million barrels per day. It doesn't include the parallel flow path here in this scenario for 3 million barrels a day. And what I would do if I have a new project is I would start with this pipeline. So I'll just go into File, Save As, and save this as my new project. Once I do that, I would go in and I would start changing the input of the pipeline values and elevation profiles and valves, CVs, and whatnot throughout my system. Once I have changed the input, then I put my flow and pressure requirements on my pumps and whatnot, and I start running the system and start tweaking values in order to get the system to work. I want to get the system to a convergible level, and that would be my starting case. Once the system works, and I've got a starting case, you can easily use the same cost information that you had in your previous project for material and installation and maybe maintenance costs or energy cost, and you can calculate the cost very easily. What you would do there is on the sizing tab, that's where you would use the middle option right here to calculate cost, do not size. What that would do is it's going to calculate if you have monetary cost information that you can input, then that will calculate what the dollar value of your initial system configuration would be. Then the idea is when you start changing your system and using the ANS module to automatically size your pipeline for your new requirements and your new details of your pipeline and your piping network, what you want to see is the cost savings. So this is one of the things that could be a potential hangup for people is having that cost information could be difficult to come by. But here's the thing, it doesn't matter. If I was to try and repackage this example for the ANS module, it's 10 years later. So those costs that were documented in the paper, it's probably not $1.50 per kilogram of piping anymore. Maybe it's $3 or $4 per kilogram. Who knows? But that doesn't matter, because what I can still do is I can take that initial cost information that I had 10 years ago, even though it's very old, I can apply it. Then let the Fathom ANS module do its thing to automatically change my pipe diameters throughout my network, find a better configuration of pipe sizes and pumps that are needed in order to meet my design requirements, and then I'll be able to see my cost savings. So even though I'm using cost information that might be 10 years old, it doesn't matter, because let's say that my original cost is $100 million based upon 10-year-old cost information, and then I allow ANS to do its sizing process, and based upon the sizing of the module, if it comes up with $30 million of savings, that's perfect. That shows that it's a much better design at that point and a really good starting point. Then you can go and get better cost information, or you can scale it up for today's cost values, and then you can start refining things more and more. And that's how you can use ANS to size your new design based upon starting from one of your designs on a previous project that you might have worked on. So that's what we're talking about here, starting from a well-engineered design, and you can save some massive amounts of costs for initial cost calculations, and then overall we saved $100 million for the future design case. And it allows you to easily quantify your trade-offs between first and life cycle cost, and how you can increase your capacity early on rather than just waiting for it later down the road. Anyway, that is today's webinar, a little bit shorter than usual. And again, where you can find the technical paper on our website is to go to aft.com. I realize I'm not showing my current screen. There we go. Go to aft.com, and then under Learning Center, click on Technical Papers. And then on the Technical Papers page, scroll all the way down and look for Optimization of Seawater Pumping System. That's the one that this was all based on. If any of you have any questions, feel free to contact us. You can reach us at sales@aft.com. And if you want to try out the ANS module and give it a run, then give us a call and let us know, and we'll be happy to set you up with that. Thank you very much, everyone, for your time today, and have a wonderful rest of your week.